Okay, let's get settled quickly, and I'll now be continuing my second part of today's presentation. And that's the NLP pipeline. So, natural language processing is naturally a sequential task, right? And a series of steps need to be carried out to accomplish this task, and we'll look into what are these different steps or processes while you are processing a particular task. Okay. So data acquisition, some of the key stages are data acquisition. That's about acquiring the text in the very first place, right? That's specifically the stage where you will be looking for data sets or creating your own, right? Uh, then we have text cleaning. All the text that basically comes from different sources are not necessarily clean or in the required format. So you would need to clean the text, especially if you are considering text from the web, then you might need to get rid of all those HTML or XML tags and other symbols that you might not need, right? And then of course you need to pre-process the text, because there are a number of things like tokenization, stemming, normalization, and all those different tasks that need to be carried out on pre-processing, so that your text are in a ready format to feed into your model, right? And then you have this feature engineering step, where you essentially determine the features that you will be considering for that particular task, right? And then you basically develop a model. Once you develop the model, you need to evaluate it for its goodness, right? Once you have evaluated it, then you deploy it, and then the final step would be monitoring and model updating. Just making sure that your model is working well, right? And whether it needs further improvements or not, right? So you have this generic NLP pipeline in figure 16 there. You have data acquisition followed by text cleaning, pre-processing, feature engineering, modeling, evaluation, deployment, and monitoring and model updating. As you can see, it's not necessarily always sequential, right? There are certain loops involved as well, right? For example, in the evaluation part, you suddenly realize that you need to improve the model, and that improvement can be done via pre-processing. Then of course you need to pre-process the data and then move ahead accordingly. Similarly, in the monitoring and model updating part, basically you realize that your data sets are not enough, not sufficiently in good number. Then of course you need to acquire more data. You need to maybe introduce some additional features or all this stuff, right? So this is basically the generic NLP pipeline here. We'll be looking at each step in detail. Data acquisition part, you may use publicly available data sets, and these days it's not difficult to get data sets as such. That's a generic statement. I would not say that you would be able to get each and every type of data set that you'll be looking for your specific problems, but in general there is a growing trend to publicly release any data sets you would have prepared, right? Even conference papers, they encourage or they ask for any data sets that you have developed during your research to be made available, publicly available. Else, if that's not the case, then you should be developing the data yourself, data sets yourself, and in that case, one of the ways could be just scraping the data, right? Scraping the data meaning preparing the data from, extracting the data from different sources. It could be any PDF documents or any available documents, or it could be some web sources, right? Web pages and all. You need to scrape the data. And the good thing about is that there are already some good tools and frameworks with the help of which you could basically scrape the data, like Beautiful Soup, Scrapy, or Spacey, and several other tools. Even the popular or very famous natural language toolkit also has certain features, right? So, as a beginner researcher in NLP, so you are highly encouraged to go through all of these different resources or books for beginner researchers, like Natural Language Processing with Python. That's written by Stephen Bird. That's a very useful book that I would suggest you to go through. That's one thing. But then there are other books as well. But that would be one very good book, because it basically has organized these different chapters in an incremental manner, right? So that it teaches you some basic things first, and then gradually it moves to the more advanced applications and all. So while you are preparing to acquire the data or develop the data, then product intervention also could be one important step. Product intervention meaning you focus on the product/feature specific data. For example, if you are trying to develop a chatbot or a customer support bot, then of course you should focus on the data sets that are applicable for this task, right? So that's where product intervention basically comes into play. At times, beginner researchers basically confuse on the appropriateness of any available data sets, and that's where you need to consult your more experienced friends or seniors, or your, let's say, professors or other researchers. All right, so that's a good point to basically do this thing. The other thing is data augmentation. So as stated earlier, deep learning, machine learning, all of these models are data hungry models, meaning to say that they wouldn't perform that well with a small size of data sets. So, but the problem is that most of the time you end up with just a small size data sets, and of course there are risks that with small size data sets your model does not generalize well, performs very poorly, right? And then you need to increase the size of the data sets. And there are different data augmentation techniques to increase the size of the data sets. And some of these techniques we'll be discussing shortly. So how do we increase the size of a data set if we have small size data sets? Let's take an example of image, because that makes it more easy to relate. So if we have, let's say, 5 images, if you just flip it 90 degrees, that could be another image of the same image, right? If you just slant it, if you make it a slight bit slanted, that could be another image. So basically, if you just change the orientation of it, change the angles of it, if you just let's say make some changes to the orientation and other stuffs, then that could already contribute to a different image, although the original image is the same. right? So that is one of the ways how you basically augment the data in image, in case of image data sets. In case of text data sets, you could also do the same thing by this synonym replacement technique, right? So you might have an original text, and what you could do is you could basically replace certain words in the original text by synonyms, right? That way you have the original text plus the newly generated text with synonyms, right? Other technique would be back translation. So let's say you are trying to develop a parallel corpus. Parallel corpus meaning this, the text in the source language, that's English, and the text in the target language, that's let's say Nepali, right? So basically, how you could improve or increase the size of the source corpus here, for example, could be via back translation. Let's say you have a text in English, and you provide it to the machine translation system. It provides certain translation based on whatever it has trained, whatever it has been trained. What you could do is now back translate the translations that are in the target language to the source language. Back translate meaning you could just translate whatever has been translated back to English in your own words. That would increase at least one more one more text in the English language, let's say. Right? So that's one way of doing that, back translation, add text that are back translation of the target translation to the source. Right? TF-IDF, that's a very popular technique in natural language processing, term frequency, inverse document frequency. Right? That's been used for spam email classification as well. Actually, it has its roots in from information retrieval or search engines, right? So based on the TF-IDF scores, based on whatever TF-IDF score, based on so if a particular term has a high TF-IDF score, then that particular term is considered more relevant to the query, or more relevant with respect to the particular document. That's it, right? One particular word occurs 1,000 times in a document, meaning to say that that particular word is significant. Of course, there is this caveat or warning or caution to be made that there are stop words. There are stop words in natural language processing, like this prepositions, of, and all these things, and articles, right? And these stop words would need to be removed first to carry out any further text processing steps, right? So back to TF-IDF. So a particular word, if the particular word occurs very frequently in a document, then that word is definitely significant with respect to the document. But if the same word occurs equally frequently across documents, right, then that word in comparison with all the documents is not that significant enough. So TF-IDF basically gives that score of that word occurring in one document alongside occurring in n documents, multiple documents, right? So TF-IDF based word replacement, you could basically replace the words based on the scores received by these different words in the corpus or text. Use TF-IDF results to replace words in the text. Results meaning not the scores, but the words which are occurring in significant or good number. Right? Bigram flipping, that's another technique. So in NLP there is this method or technique known as n-gram model. N-gram model. N-grams. Gram basically refers to a letter or a word in the text, right? So if it is, you just replace the value of n with a particular number. If it is 1, then that's a unigram, that you are considering just that particular word. If you are replacing that n with 2, that's 2 grams, then you are considering 2 words. That one particular word and then a preceding word, 2 grams, right? If you are replacing that value of n by 3, then that's 3 grams. That particular word in consideration and 2 words preceding that word, that's trigrams. And that basically you can keep on increasing that value, but in general, due to processing capabilities and then all the complexities, it's advised that you don't necessarily go beyond trigrams in text processing. That's the situation, right? So bigram flipping means that let's say add text. This word add text, phrase add text, that's a 2 grams, right? And we have add and then text. That's the following word is text. So by bigram flipping, you could just reverse the order of the words. Text add. Not add text, but text adds. Right? So that also contributes to data augmentation. Okay? Replacing entities, add text with replaced entities. So you might have an article about, let's say, article which mentions quite a bit of times about London or New York. You could basically replace those entities by, let's say, Delhi or Kathmandu or so on. And that way, you could basically also contribute to data augmentation. Adding noise to data. Sometimes that might also be helpful. Noise meaning, we are just trying to add some words with similar spellings. That's considered to be a noise because compared to the original text, of course, that's an addition from your side. So that's a noise here. Advanced techniques. There are other advanced techniques like snorkel, right? So snorkel, which builds large training data automatically without manual labeling, using heuristics and creating synthetic data by transforming existing data and creating new data samples. That's a snorkel. Easy data augmentation and NLP org. These are libraries for creating synthetic samples for NLP. Active learning approach, where algorithm interactively queries a data point and gets it labeled. Right? So these are also some of the different techniques that you could employ for data augmentation in case of small data sets. Okay, so after data acquisition, that's the stage where you create or develop your own data sets or acquire a publicly available data set. The next stage would be text extraction and cleanup. Text extraction and cleanup, once you have acquired, let's say the assumption is that you are preparing your own data set here and not really using the publicly available data set. Text extraction and cleanup, so this involves just extracting raw text from the input data by removing all the other non-textual components or information such as markup, metadata, etc. But mind it, sometimes you might need metadata as well. In that case, you need to be careful. Because in our own research, we were scraping online news articles, and in that context, the publisher information and the date it was published, date of publication, these are metadata, and these were important. These were required for our purpose. So of course we wouldn't remove those metadata, rather retain those metadata. And then converting the text to the required encoding format. Right? There are often issues about encodings. Right? Because if the encoding is not right, then you won't be able to understand the text. Right? For Nepali, it's basically UTF-8. Nepali. It's basically UTF-8, that's Unicode, right? So please take note of that. And under text extraction and cleanup, you need to do some HTML parsing and cleanup, right? For that, I already mentioned you could either write your own HTML parser or use existing libraries. That's a beautiful soup or scrapie. Unicode normalization, right? So these days, particularly with online social media text or tweets or statuses, right? It's quite common to have not just the text but emojis as well. There are a lot of emojis in the text as well, right? And for the machine to process those emojis, those emojis need to be converted to their respective codes, right? And we have a unique code for those, Unicode values for those emojis as well, right? So, text encoding and conversion to machine readable formats, for example, emojis, right? It could be LOL, or it could be a smiling, angry, and all those stuffs, right? It could be Santa Claus, it could be something else, but that needs to be that emoji needs to be converted in the text, in the Unicode value for the machine to understand and process it. Several encoding schemes exist, and default encoding could be different for different operating systems. So please take note of this one, right? It could be different for different operating systems. Okay. These text, when they come from different sources, there is a high likelihood that these texts contain typos or spelling errors. So this needs to be corrected in the first place. So spelling correction would be the other step, that sub step that would come under text extraction and cleanup. There could be certain systematic system specific errors. For example, if it is an output of automatic speech recognition, right? That is essentially speech converted to text, and those text or transcriptions, there may be some errors in that, right? There may be some errors in that, so that has to be processed and cleaned. Similar, let's say you performed an OSHIA, that's optical character recognition. You scan the text, you have a picture image, and then using an optical character recognition software, you converted that into text, editable text. There too, there could be some certain spelling errors or other unnecessary symbols that might have actually crept in due process. And that needs to be cleaned via post-editing. That's post-editing, right? Post-editing meaning editing on the output of the ASR or OCRs. Next is pre-processing. Now that you have the data, you have almost cleaned everything. You have a clean data. You have well-formatted data, right? Still, it's not yet ready. It's not yet ready to fit to the model. There are certain things that you need to do, that you carry out as a pre-processing step. And sentence segmentation and word tokenization are some of the preliminaries, some of the preliminary pre-processing operations that you do for most of the NLP tasks. Most of the NLP tasks. Frequent, then there you have some certain frequent steps that you basically do time and again. These are stop word removal. I already gave you an example of stop words. But this is not something this is not a fixed rule that you always need to remove the stop words. For certain NLP tasks, you might need to retain the stop words as well. Because if you remove the stop words, then the data might not be in that format which is required for that problem. Okay? So please note that as well. Stemming and lemmatization, so that's about reducing the word into respective stems, affixes, and the lemmatization, reducing it in the lemma form or base form, right? Removing digits removing digits and punctuations. So if you don't require digits or punctuation, you need to remove it. and then you need to change the lowercase and uppercase. In case of Nepali, we don't have lower and uppercase, so we don't have that issue here, right? There are other steps as well in the pre-processing step, which is normalization. Normalization. Let me give you an example. If you have this word 1964, and then you are preparing this data for, let's say, text to speech problem. In that case, depending on the context in which that particular word occurs, you will need to normalize that differently. 1964, if that occurs in the context of a year, that's 1964. So you need to type in 1964. If that occurs in the context of a currency, money, then you need to normalize that text as 1964. That's a part of normalization. I can give you another example. So shorthands, right? Shorthands is very common in, let's say, this social media, chatting, and other areas, right? The computer would not understand LOL, right? So you need to expand that. You need to expand that as laughing out loud, right? So that's a part of normalization. So there are plenty of other examples. So let me stop it here. But that's one. And the other thing is language detection. So these days it's very common to have different forms of text, right? It could be a transliterated text. Romanized people type in the Romanized English, right? Some people type in Romanized English. Some people type in Nepali. Some people type in English. So we could have at least, let's say, just as an example, you could have at least 3 different forms of text. One could be in Nepali, one could be Romanized English, one could be in English, plain English. Right? One could be something, maybe somebody wants to write in Hindi as well. So see, in the same text, we have 4 different types of text. So other important part is language detection, of course. Language detection, right? There was an issue. I think it's solved now. What happened is that Hindi and Nepali are very similar languages in that we use Devanagari script, right? So earlier, when the Google didn't have this language detection thing implemented, right? It would say like, "Aapko swagat hai," right? It would display that, even for a Nepali user, right? Thinking that that person is necessarily from India or something, or speaks Hindi or knows Hindi, right? So that's a part of language detection. That's part of language detection, right? And the interesting part is Hindi and Nepali both use the Devanagari script. The script looks similar and everything. But then the question is, if the script is the same, then how do you identify the whole text is in Nepali and not Hindi? Based on? Louder? Well, grammar, I mean, that's also one thing, right? But grammar, that's one thing. But, there are certain words that are specific to Nepali, right? And not Hindi. So if the system does, let's say, word analysis of these different words, then tentatively it can say, okay, this is in English, or sorry, this is in Hindi, or this is in Nepali, right? Given that it is not a mix of Hindi and Nepali. Given that the text is not a mix of Hindi, if it is a mix of Hindi and Nepali, then that's difficult. And in that case, we need to apply, parallelly these code detection modules. Okay. Code mixing, that's code mixing. When we mix two or more languages, right? And transliteration. Transliteration meaning that, the Romanized English, for example, if you just type everything in English, but that's necessarily a transliteration of English, right? Yeah. Okay. Then we have this advanced processing, which involves parts of speech tagging. Earlier I was giving you an example of parsing, right? And parts of speech tagging is a core of parsing, right? Without the parts of speech tagging information, you wouldn't be able to conduct the syntactic analysis and parsing, right? Parts of speech tagging, that's assigning parts of speech, noun, verb, whatsoever, to each word, and then parsing, developing parse trees, right, to make sure that the text is syntactically correct, right? And as I said, I mean, it also gives you some preliminary information about certain meanings being conveyed by that parse tree or by that particular sentence, because the same sentence could be ambiguous. Right. Core reference resolution. So that's another interesting problem. So in text, in any text, so what happens is that it's not that you repeat the name of the entity every time, right? Ram went home, then you don't necessarily repeat the same entity. Ram did this, Ram, all those things. Right? Basically, what you do is once you have that Ram mentioned somewhere, then you replace that reference, that core reference, with some pronoun, suitable pronouns. But the problem with that is, in natural language processing, you don't necessarily always refer to the same entity. You could refer to multiple entities. Sometimes you might talk about one politician, and at a later stage, you might talk about some other politician, right? And then, as you write on certain things about those politicians, you basically also use pronouns, right? And it's important to find out which pronouns basically refer to which named entities. And that's basically core reference resolution. That's still an open research problem in natural language processing. Many researchers have worked on that, but that's still an open research problem, meaning to say that it's still a hard problem. Once you have done the pre-processing part, now you move to stemming and lemmatization. That's quite obvious because we have discussed a bit about it, so I'll just skip that part. And here are some examples of stemming and lemmatization, right? If I provided the word adjustable, the stem would be adjust. If you are provided the word better, the lemma would be good. Okay. So there are other pre-processing steps. I've already discussed a bit about text normalization. The other thing is about expanding abbreviations as well. Right. Usually, there are different markers. There are different markers like full stop, period, let's say, or question mark, or exclamation, or different markers which basically mark the end of a sentence, right? So if we basically use that knowledge for sentence tokenization, then sometimes we run into problems because there are abbreviations. There are abbreviations in English, like DR, doctor, followed by a full stop, right? And hence, that DR, in order to avoid such mishaps, we need to expand those abbreviations. Also, new work, it's a one entity, right? One entity, but there is a space. between these two words, new and work. New and work, there is a space. And if we don't provide certain information or knowledge to the system, it would essentially tokenize those as two words, two different words. Right? So those are some of the things that needs to be done under text normalization. Yeah, language detection, there are libraries like Polyglot, which could be used for this language detection. Code mixing and transliteration, I have already discussed. There are certain advanced pre-processing steps as well. So as you see in this figure, so if you just tokenize the text via sentence tokenization, you get the sentences. One sentence per line. Then that particular sentence could be subject to these different basic pre-processing steps like lower casing or upper casing, removal of punctuation, stemming, lemmatization. These are the basic pre-processing operations depending on your problem, on your specific problem, right? So you could employ parts of speech tagging, parsing, co-reference resolution, among others. So these three different steps are considered to be advanced pre-processing steps. So the next part in the NLP pipeline, next step is the feature engineering or extraction part, right? Feature engineering extraction part. So as I mentioned earlier, so in text processing, potentially every word is an attribute or a feature. Every word can be a feature or an attribute, right? So feature engineering extracts set of methods that capture the characteristic of the text into a numeric vector that can be understood by the ML algorithms. What are the features that basically describe an apple? Versus what are the features that describe a banana? Apple and banana are unique in their own forms, right? It has a shape, its color, and all those stuff. The same thing could be applied to text as well. Maybe parts of speech, TF, IDF, right? And other maybe something. Maybe n-grams, right? All those those could be different features there. So in the classical NLP or ML pipeline, what feature engineering draws is converts the raw data into a format that can be consumed by the machine. Right? The transformation functions are usually handcrafted in the classical ML pipeline, aligning to the task at hand. So handcrafted meaning that we basically develop by hand, manually, these features. Okay, we just given a problem, given a spam classification, let's say. We have a spam email classification, that's the problem at hand. And say, okay, what are the features that make this particular email a spam? If maybe there is a marketing term, right? If they announce that you won a prize or something, if they are asking for some money, right? If they are promoting some products. So these are some of the features, right? Some of the characteristic attributes that could potentially serve as features, right? So features are heavily inspired by the task at hand as well as domain knowledge. So as I gave you the example of spam classification. So that was an example, and I give you some ideas how the features could be handcrafted or basically sorted out or determined, right? So major advantage of handcrafted features is that the model remains interpretable. It's not a black box anymore. You know exactly what features you provided, right? And because of those features, you know exactly why this email was classified as spam. You know that. But if you were not necessarily doing this handcrafted, you just relied on some, let's say, deep learning model or something, you wouldn't necessarily know which features were basically, considered for that classification. It is possible to quantify how much each feature is influencing the model prediction if it is a handcrafted model. handcrafted features. Now let's look at the DL pipeline. That's the deep learning pipeline here. The main drawback of classical ML models, that's handcrafted, means you need to take a lot of time to develop these rules, right? Is the feature engineering part. So feature engineering part is quite tedious in this classical NLP ML model, right? So handcrafted feature engineering becomes a bottleneck. In order to develop handcrafted features, you need to be an expert in that field, right? Yeah. That becomes a bottleneck for both model performance as well as model development cycle. In the DL pipeline, that's the deep learning pipeline, the raw data after pre-processing, of course, is directly fed to the model, and the model is capable of learning features from the data. More of a, let's say, without you not intervening in that, right? Maybe the context and everything would be considered, right? And based on that, it will learn the features. However, since all these features are learned via model parameters, of course, in a deep learning model, what you essentially do is you just fine-tune the hyperparameters, right? Do some changes here and there, right? Some change the learning rate, maybe dropout rates and all those things different. You maybe increase the layers, right? So since all these features are learned via model parameters, the model now loses interpretability. It serves as a black box now. It's just difficult for you to basically say what's happening because of what. So this is the NLP pipeline. We have a classical NLP on one side, and we have a deep learning based NLP pipeline on the other side, right? In the classical NLP, as you can see, we have documents which undergo pre-processing, right? Pre-processing steps where we have tokenization, parts of speech tagging, stop word removal, and so on, followed by the modeling step, in which we have this feature extraction, right? Feature extraction, we have the modeling part, right? And then we have this inference, right? So your model has to infer, right? Given a new unseen data, your model has to infer and classify it, right? And then we have as output, this different tasks, like sentiment analysis, classification, text classification, entity extraction, translation, and topic modeling, and so on. That's the typical classical NLP pipeline, NLP ML pipeline. Whereas in deep learning based NLP, we have documents again. And that's passed to the pre-processing component module, and then that's basically passed to the input, where, I mean, not to the input, but it's in the form of, it's converted in the form of dense embeddings, right? Obtained by a word to vec, doc to vega glob, right? That's, I mean, before passing it to the as input to the hidden layers. So we basically conduct such transformations, representations, right? That's passed to the hidden layers, and in the output units we have these different outputs. Again, sentiment classification, entity extraction, among others. Okay. So now that we have discussed this feature engineering and extraction, the next thing is modeling, of course. Right? You need to develop a model. So the suggestion here is that you start with simple heuristics. You start with simple heuristics because that way you would essentially know what's going on, how is that model built, right? Which parameters basically influence the prediction of the model, and so on. Create a feature from your heuristics for your ML model. Pre-process your input to the ML model, apply available NLP techniques before feeding your input to the ML models. Don't directly feed your input to the ML model without some sufficient NLP pre-processing. And once for the building the model, there are different ways you can ensemble and you can stack, right? Meaning to say that in ensemble modeling, for example, you can have different models or different classifiers, right? And what you do is you basically try to combine the outputs. Try to combine the outputs in ensemble modeling. So, and then you take the average or something like that. Whereas in stacking, it would be the output of one particular model would be an input for the other model, right? So that's ensemble and stacking. And then of course you'll go for some better feature engineering, because you realize that there are certain other gaps that needs to be taken care of. Earlier I was talking about transfer learning, where you basically employ a model developed for one purpose to process other NLP tasks, right? And you reapply the heuristics, of course, to develop models so that they get improved. So model ensemble and stacking. So we have the training data in here. We have the training data, and we have three different models, right? And they basically three different models, and they basically have different, let's say, different levels of outputs and all these things. That is basically passed to the input to level 2, right? And then, that is then passed to the meta model, right? So the input of meta model is necessarily the ensemble of this level 1 models, right? And we have this final output as final prediction, whether that's a spam or ham or spam or ham. Okay? So model ensemble and stacking, that's one way of doing things. The final stage, we are now moving to the final stages. So that's the model evaluation, because even in our daily life, let's say if you cook something, then you need to provide a feedback, or you need to evaluate how good you have cooked, right? So there are two types of evaluation. You prepare a soup, chicken soup, right? You test it while preparing, and you realize that there is a little bit of less salt. Then you add it. Then that's formative evaluation. That's formative evaluation or intrinsic evaluation, right? But once you have prepared the soup and you give it to the client, or you give it to your parents, or you give it to your sister or brother, and then that mode of evaluation is already extrinsic or summative evaluation. All right. So you have heard about these different evaluation metrics for any NLP task: precision, recall, F1 measure, F measure, and all those things. They essentially are related to intrinsic evaluation. Right? And extrinsic evaluation is about how satisfied you as a client are on the actual results. That's extrinsic evaluation. Okay. So intrinsic evaluation focuses on measuring the system performance using precision and recall. Extrinsic evaluation focuses on evaluating performance on the final objective. We have this final component in the pipeline. That's post-modeling phases. Right. Once that's to do with when you have tried and tested your model, now it's ready for deployment, right? And deploying phase, this post-modeling phase involves deploying the model, monitoring the model, and model updating. Right? You update the model as required. Right. So as you can see, in the NLP pipeline, there is a whole lot of processes happening behind the scenes. Right. So, and then you need to consider doing all these different things in the pipeline before you can actually get the different results. So that was about the NLP pipeline. So if you have any questions in here, I'm ready to answer those. And then we will move to the final part.